In this lecture, you'll learn about the IP address classes. We're going to cover classes A, B, and C here, which are used for allocating addresses to our hosts. And then in the next lecture, we'll cover classes D and E. Okay, the first thing to talk about is the effect that that line has, which designates where the network portion of the address is and the host portion of the address. If a subnet mask is a /8, for example, using the first 8 bits for the network portion of the address, then 8 bits for the network portion, 24 bits for the host portion. If we compare that with a /24, we're going to have 24 bits for the network portion and only 8 bits for the host portion. So we could have a /8 is going to have not many networks, but a lot of hosts per network, or a /24 would have a lot of networks, but not many hosts per network. So we've got a trade-off whenever we decide where that line is going to be about how many networks we're going to have and how many hosts that we're going to have. Okay, let's talk about how internet addressing was originally supposed to work. Because when IPv4 was first conceived, the designers didn't know about what was going to happen with the internet. They didn't realize that there would be a huge explosion of usage and everybody would be using it and that everybody would require an IP address. So when they first designed it, they designed it for what was right at that time. And as we go through this section, you need to think about the internet, about how it was then, to understand why IPv4 was designed the way that it is. There's a few issues with IPv4 that you'll learn about as we're going through this section, and those issues came about because the designers didn't realize what was going to happen in future. So as long as you think about it from that point of view, then everything should make sense. So the original way that IPv4 addressing was meant to work, when a company wanted to communicate on the internet, they would apply for a range of IP addresses. Now, the global assignment of IP addresses is handled by IANA. That stands for the Internet Assigned Numbers Authority. So they are up at the top level looking at it from a global point of view. They assign large blocks of addresses to the local authorities in different regions. So a company, they would apply to their local authority to get a range of public IP addresses. If they had 6,000 hosts, for example, they would ask for a range of IP addresses big enough to cover that, plus some room for growth in the future as well. That company would then allocate those addresses to their hosts in their different offices. Unfortunately, when IPv4 was created, the designers didn't realize how big the internet was going to get, like we were just saying, so they didn't create a big enough address space. There's not enough IPv4 addresses for every host that actually needs an IPv4 address that's going to be communicating on the internet. So IPv4 ran out of addresses. The long-term solution for the problem is IPv6, which has got a much bigger address space. IPv4 is a 32-bit address, IPv6 is a 128-bit address. And we're going to be talking about IPv6 in a lot of detail in a later section. Private IP addresses with NAT, which is Network Address Translation, are, however, currently deployed in the majority of enterprise networks as a workaround. So IPv6 is the long-term solution, but today, private addresses with NAT is actually more commonly deployed. But as time goes on, there will be more uptake of IPv6. Again, we're going to discuss private addresses, NAT, and IPv6 in a lot more detail as we go through the course. But as I was saying, to understand the next few lectures, don't think about private addressing, NAT, and IPv6 yet. We're going to get to there later. To understand why we have those and how they work, you need to understand the original implementation first. So that's what we're going to cover first. So Class A addresses. The Internet authorities split the global IPv4 address space into separate classes. Class A addresses are assigned to networks with a very large number of hosts. So Class A, there's going to be a small network portion and a large host portion. The high order bit, which is the first bit in a Class A address, is always set to 0. And if you look down in the bottom left at the address there, you see I've highlighted the first bit. It's always going to be a 0 in a Class A address. With Class A addresses, the default subnet mask is a /8, so 255.0.0.0, and valid network addresses range from 1.0.0.0 to 126.0.0.0/8. So that's the network address. The actual host address ranges from 1.0.0.0 to 126.255.255.254. So 1 to 126, that allows for 126 networks. And if you counted up the host bits, 24 to the power of 2 adds up to 16,777,214 hosts per network. Now, you maybe noticed there, if you actually counted this up, the available values, if you set the first bit as 0, would actually be, we could have all zeros, and we could go up to 127. But all zeros and 127 are not in the valid address range that we can assign to our hosts because they are reserved addresses. 0.0.0.0/8 is reserved and signifies this network, and it's used by some protocols. So 0.0.0.1 to 0.255.255.255 are not valid addresses that you can assign to hosts. That entire range is not available. Also, 127.0.0.0/8, which is also in the Class A space, is also reserved. That is used as the loopback address, and it's used for testing the IP stack on the local computer. So 127.0.0.1 to 127.255.255.255 are not valid host addresses. So you see I've written down at the bottom here, whoops, they just wiped out over 33 million addresses that could have been used for addressing actual hosts on the public internet. If you think about it, this network, they could have just used a single address for that, like one address rather than 16 million addresses. And the same for the loopback, they didn't really need 16 million addresses to be used for loopback testing. And if you're thinking, well, there's this huge shortage of addresses on the internet, why would they do something crazy like that? But the reason is, when IPv4 was designed, they didn't realize that they were going to run out of addresses. So they thought, hey, it's no problem. We can assign 16 million addresses for testing. It doesn't matter because we don't have a shortage of addresses. They didn't realize what was going to happen later on. In fact, let me give you a demo of using the loopback. So let me open up a command prompt here on my laptop. And if I did an IP config, again, I've got loads of virtual adapters on here, but if I scroll up slowly, you'll see I don't have the IP address 127.0.0.1 assigned to any of my network cards in here. It's built in with IP. So I can ping 127.0.0.1, which is the loopback address, and you see I'm getting a reply, which means it's up. The reason you do this is to test that TCP IP is working on the local machine. If you wanted to check, say that you're in New York and you want to check that you've got connectivity to a server in Boston, you could ping that server. There's not much point in pinging the server in Boston if you can't get to your local default gateway router in New York. So you would ping that first. And also, there's not much point in pinging the local router if TCP IP isn't even working on your laptop. So the way that you verify that TCP IP is up and running on your laptop is by pinging the loopback, and we can ping 127.0.0.1. But like I was just saying, it's the entire Class A range beginning with 127 that is actually reserved for testing loopback. So I don't have to ping 127.0.0.1. I could ping 127.100.200.50, and this is going to work as well. So I can ping anything beginning with 127, and it's going to check the local TCP IP stack. So it's good to have that address for testing, not so good that they took out an entire Class A network for it. Okay, so you see that all zeros would begin with 0, obviously, and 127 is 0 and then all ones. Class A always begins with a 0 as the first bit. Okay, now, obviously, a company that had a Class A address would not put all 16 million hosts into a single logical network. That would be terrible for performance and security. They would split that big /8 range up into smaller subnets and assign those to their different departments in their different offices. For example, if they received the Class A address 15.0.0.0/8, they could allocate the subnet 15.0.1.0/24 to sales computers in New York, 15.0.2.0 255.255.255.0 to accounting, that was just the same /24 in dotted decimal notation, and 15.0.9.0/24 to sales computers in Boston. So they would have that huge network that they got assigned by the internet authorities, and they would split it up into smaller subnets that they could assign to their different offices and their different types of hosts in different offices. And when you do that, it's called subnetting. You're going to master subnetting in a later lecture because it's super important. Okay, we covered the Class A addresses. Next up is Class B. So Class B addresses were originally assigned to medium to large-sized networks. With Class B, it's the first 2 bits in the address are always going to be set to 10. Class A addresses default to a /8, which is the first octet. Class B subnet masks always default to a /16, which is the first 2 octets. And the valid network addresses range from 128.0.0.0 to 191.255.0.0. Again, this is a Class B. The subnet mask is the first 2 octets, so the ranges use the first 2 octets. So 128.0 to 191.255. That allows for 16,384 networks and 65,534 hosts on each of those networks. Again, you would never have a flat subnet with up to 65,000 hosts in there. If you were given a Class B network in the real world, again, you would subnet it into smaller subnets. The last class that we'll cover here, the last one that can be used to assign addresses to hosts, is Class C. And this is used for small networks. You saw that Class A, we've got the first octet, so /8, is used for the subnet mask. Class B, the second octet, it's a /16. And with Class C, the default subnet mask is a /24, up to the end of the third octet. And with Class C, it's the first 3 bits that are important. They're always set to binary 110. The valid network addresses range from 192.0.0.0 to 223.255.255.0. That allows for a little over 2 million networks and 254 hosts per network. That's something that you're going to know by heart later on. A Class C network has got 254 hosts up to that amount. With a Class C, that's small enough that that could be allocated as is for a real world deployment, or again, if we wanted to, we could actually subnet that into smaller networks as well. A quick note on private addresses now. So I gave you all the addresses that were available in our Class A, B, and C networks, and we spoke about the reserved addresses for our loopbacks, and also the addresses beginning with 0 are reserved as well. There's also a range of reserved private addresses in each class. Those are valid to be assigned to hosts, unlike the other reserved addresses, but the difference is that these ones are not routable on the public internet. So these were originally designed for hosts in a closed private network that should have no internet connectivity. For example, imagine you've got a high school and you've got students there that need to work on PCs, but you don't want them to be able to browse the internet. You would put them on private addresses. The benefits you get from that are that they can't get hacked because they're not connected to the internet, and also it doesn't cost you anything. You have to pay for public IP addresses. Private IP addresses are, of course, free. The different ranges that are used for our private addresses: in Class A, it's 10.0.0.0 to 10.255.255.255 on the host addresses. The private host addresses in Class B, 172.16.0.0 to 172.16.31.255, and the Class C private range, 192.168.0.0 to 192.168.255.255. Again, when you're experienced with working in networking, these are things that you're going to know off the top of your head. Private addresses, there's quite a bit more we need to talk about with those. That's going to be covered in a later lecture in this section. So you saw in the last lecture that classes A, B, and C include all the addresses that are valid to be assigned to our end hosts. And those addresses went up from a 1 in the first octet up to 223. But you're maybe thinking, what about 224.0.0.0 to 255.255.255.255? Because you know that the maximum value in each of our octets is 255. We only went up to 223. Well, the next class is Class D. And Class D is used for multicast addresses. You'll learn about what multicast is right on the next slide. With Class D, the 4 high order bits, the first 4 bits in the first octet, are always set to the binary value of 1110. We can actually count this up. If you look at the first octet down in the bottom left here, we've assigned the bits 1110. A Class D always begins like that. So if we add these up, 128 plus 64 plus 32 is 224. So the lowest address is going to be 224. And then the remaining bits over to the right are 8, 4, 2, and 1. If we add those up, it adds up to 15. And 224 plus 15 adds up to 239. So that's where we get the range of 224 to 239 from. These Class D addresses were not allocated to hosts, and there's no default subnet mask. They're used just for multicast traffic. So to see how multicast works, let's do a quick review of Unicast first. I've got my sender over on the left, which has got the source IP address 10.10.10.10, and it's going to send traffic to destinations at 10.10.10.15 and 10.10.20.15. So it sends traffic to 10.10.10.15, and if you looked in the packet in the layer 3 IP header, you would see the source IP address is 10.10.10.10, the destination is 10.10.10.15. And if we're using a /24 subnet mask, they're both in the same subnet, so that traffic can go directly between the hosts without having to go via a router. Let's say that the host then sends traffic to the other host up in the top right. Let's say that this is a video stream that we're sending again. So we've unicast it to 10.10.10.15. We then unicast it to 10.10.20.15 as well. If you look in the IP header, again, unicast traffic, the source address is 10.10.10.10, the destination address is 10.10.20.15. Again, we were using that /24 subnet mask, so they're on different networks, so the traffic is going to have to go via a router. And if this was video streaming we were doing here, it's 2 completely separate pieces of traffic, so it's going to use 2 meg if it was 1 meg per stream. Now, we can improve this by using multicast traffic. With multicast traffic, we're going to send 1 copy of the traffic from 10.10.10.10, and that 1 copy is going to get sent to 10.10.10.15 and 10.10.20.15 as well. We're going to run an application on the sender, which is going to send it as multicast traffic. And in our example, we're going to send it to a destination multicast address of 239.0.0.1. It still comes from the same source address of 10.10.10.10, and the destinations still have their normal unicast addresses there as well, but we send it to this special multicast address. That will then go to all of the hosts that were interested in getting that traffic. Now, a good analogy of this is you can think of it like tuning into a radio station. So on most hosts, 10.10.10.15 and 10.10.20.15, they ran an application on there that said they wanted to receive the stream for 239.0.0.1. Now, as long as you've configured support for this on your routers, that traffic will get forwarded to all of the hosts that are interested in receiving it. And the benefit you get is, example here, we're only sending 1 meg's worth of bandwidth rather than 2 meg. And if there was 50 interested hosts, it would still just be 1 meg worth of bandwidth rather than 50 meg. So you save a lot on the bandwidth that you're using. It makes things a lot more efficient. Moving on to Class E addresses, they are experimental and reserved for future use. The first bits in a Class E are always set to 1111. So again, if we count it up, that's going to give us the possible values of 240.0.0.0 to 255.255.255.255. Just like our Class D multicast addresses, these addresses do not have a default subnet mask. There is one special address that is actually used in Class E, which is the broadcast address of 255.255.255.255. That is the broadcast address for this network, meaning whatever network the source is on, it's a broadcast for that network. Actually, while we're talking about broadcast traffic, let's just go back to the previous slide for a minute, and I'll explain further about why multicast is different and can be more efficient than broadcast traffic. Notice in the example here, on the local subnet, the hosts that are attached to the switch, it only went to the top host at 10.10.10.15. The traffic did not get sent down to the host below that at the bottom. If this was broadcast traffic, it would be sent to all hosts on that subnet, not just the ones that wanted it. So multicast is more targeted, it's more efficient. Another difference is that as long as you've configured your routers to support it, routers will forward multicast traffic. So that's how we were able to get it to the host up in the top right. Broadcast traffic does not go outside its own local subnet. It does not get forwarded by routers by default. Okay, so that was our Class D and our Class E addresses. These Class E reserved addresses, they're never really used. You need to know what they are, and particularly for the CCNA exam, but real world, you'll never come across Class E addresses. They're not used in production environments. Class D addresses are used if you're using multicast. Okay, so that was our Class D and our Class E addresses. Let's just have a look at a summary of the different classes before we move on. So Class A is 1 to 126 in the first octet. The default subnet mask is a /8. Class B is 128 to 191, and that defaults to a /16. Class C is 192 to 223, and that defaults to a /24. Classes A, B, and C are the classes that can be assigned to hosts. Class D is for multicast. That uses 224 to 239. And Class E is experimental. That's 240 to 255. You want to have these classes committed to memory, not just for the CCNA exam where they're completely essential, they're also completely essential for real-world networking as well. Thanks for watching. If you want to get hands-on practice with Cisco networks for free, then you can download my 400-page CCNA Lab Guide, which you can see above my head right now. Also, check out the video about my CCNA course. It's the highest rated course online. Thanks.